Okay, welcome again in my online sessions on pharmaceutical analysis. This time we will discuss some multiple choice questions on pharmaceutical analysis, particularly on IR spectroscopy. Now look at the question: which of the following molecule is not transparent to IR radiation? When the question is not transparent, it means which of the following molecules absorbs the IR radiation. Now, what is the criteria to absorb IR radiation? That is, there should be some change in polarity, and there must be some natural vibrational frequency with a particular molecule, and when it matches with the IR radiation, then it absorbs. Now, symmetric diatomic molecules, they are transparent to IR radiations. Now if you look at the options given, this is oxygen, it is symmetric diatomic molecule, O2. Nitrogen, again it is symmetric diatomic molecule. D2, deuterium, it is again symmetric diatomic molecule. Whereas this, look at this, carbon dioxide, it is not symmetric diatomic molecule. So, which of the following molecule is not transparent to IR radiation? In other words, which of the following molecule absorbs the IR radiation? The answer is CO2, because it is not transparent. Moving to the next, which of the following molecule absorbs IR radiation? The similar type of question asked in different words. Look at this, the options given: KBr, NABr, LIBr, potassium bromide, then sodium bromide, lithium bromide, and methyl bromide. Now see, these three are inorganic salts. There is no permanent change in dipole moment with respect to this KBr, NABr or lithium bromide. So they don't absorb IR radiation. This particular salts are used to construct the optical components of the IR instrument because they are transparent to IR. But here, methyl bromide, it contains functional group. It contains bonds like CH, CBr, like this. So, because these functional groups, these particular bonds have some natural vibrational frequency and they can absorb the IR radiation. So the answer is CH3Br4. Next one, in symmetric stretching vibrations in the molecule, there is change in bond length, bond angle, both bond length as well as bond angle, and none of the above. Now we know that this IR spectroscopy is based upon molecular vibrations. The molecular vibrations are of two types: stretching vibrations and bending vibrations. Now when there is a stretching vibration, the change in bond length takes place. And in case of bending vibrations, change in bond angle takes place. Now if The structure is like this. Say carbon H, like this. If there is a CH stretching, in this case, this carbon and hydrogen gets stretched. The bond length changes, and when there is a bending vibration, then there is a change in bond angle. This is a bond angle and this is bond length. So when there is a stretching, the change in bond length takes place. In this case, one atom moves away from the another atom. Likewise, so this is a kind of a stretching vibration. Moving to the next, in plane scissoring, vibration in the molecule alters. A similar question as earlier. When there is a scissoring is a kind of bending vibration. When it's a bending vibration, there is a change in bond angle. So earlier we have discussed earlier with respect to earlier question that a stretching alters bond length while bending alters bond angle. This in plane scissoring is a kind of bending vibration, so there is a change in bond angle. Next one, how many number of vibrational modes are possible in water molecule? Now if you consider water molecule, look at this: oxygen, hydrogen and hydrogen. This is a water molecule. In this molecule, whether it is linear or non-linear, this is important component here. In case of linear molecule, the number of vibrational modes are given by the equation 3n minus 5. And in case of non-linear, like water, the number of vibrational modes are 3n minus 6, where this n stands for number of atoms in that particular molecule. This water molecule contains 3 atoms, so this is 9 minus 6. It is equal to 3. So because water is non-linear molecule, the number of vibrational modes as per this equation is 3. So the answer should be 3. Moving to the next, how many number of vibrational modes are possible in carbon dioxide molecule? Now when we look at the structure of carbon dioxide, carbon, C double bond O and C double bond O. This is your carbon dioxide molecule. Now this carbon dioxide is a linear molecule. This is a linear molecule. And as per earlier equation, in case of linear molecule, number of possible vibrational modes are given by the equation 3n minus 5. When it's a 3n minus 5, that is 9 minus 5, that is equal to 4. So in case of carbon dioxide, because it is a linear molecule, number of vibrational modes comes to be 4. Likewise, the number of vibrational modes are decided by whether your molecule is linear and non-linear and a number of atoms involved in that particular molecule. And as I told, for linear molecule, number of vibrational modes are given by 3n minus 5, and for non-linear, it is given by 3n minus 6. So this is the basis for calculation of vibrational modes in the molecule. And look at this question. This is very interesting one. The IR absorption frequency of carbon-carbon double bond and carbon-carbon triple bond is. Now look at this. This is carbon-carbon double bond and this is carbon-carbon triple bond. If you look at this is carbon-carbon triple bond. Now the question is, look at the question, the IR absorption frequency of carbon-carbon double bond is. Now what will decide the absorption frequency? It will be decided by a natural vibrational frequency of the molecule. So what is natural vibrational frequency? That is V bar is equal to 1 upon 2 pi C under root K by mu. So this natural vibrational frequency is given by this equation, 1 upon 2 pi C under root K by mu, where this 1 upon 2 pi C is constant, the K is force constant and mu is a reduced mass. So K is a force constant and mu is a reduced mass. Now this force constant means this natural vibrational frequency V bar is directly proportional to the force constant. Now this force constant is governed by a bond order. If bond order is higher, force constant is higher, natural vibrational frequency is higher and IR absorption frequency will also be higher. Now if you compare a bond order between carbon-carbon double bond and carbon-carbon triple bond, the carbon-carbon triple bond is higher bond order than this. So when bond order is more, force constant will be more, natural vibrational frequency will be more and IR absorption frequency will also be more. So the answer is this. In case of carbon-carbon double bond, the frequency will be less than in carbon-carbon triple bond. Right? So because in carbon-carbon triple bond, bond order is higher, force constant is higher, so natural vibrational frequency is higher and IR absorption frequency also will be higher. Moving to the next. The natural vibrational frequency of particular functional group is dependent on. So what decides natural vibrational frequency? Again come to the equation earlier discussed. V bar, this is natural vibrational frequency, is given by 1 upon 2 pi C under root K by mu. This is equation for natural vibrational frequency. Now this is pi is constant, C is constant, so the K and mu. What is K? It is a force constant. The force constant will be decided by bond order. So natural vibrational frequency will be governed by bond order. Now what is mu? It is a reduced mass. Reduced mass. And this reduced mass is equal to m1 m2 upon m1 plus m2. m1 m2 upon m1 plus m2. That is atomic mass of first atom and atomic mass of second atom. That is m1 and m2. So reduced mass will be calculated from atomic mass of all the atoms involved in the bond formation. So here the bond order, it is also deciding factor for natural vibrational frequency as well as mass of the atoms. The both things are involved in deciding natural vibrational frequency of particular functional group. So the answer is both 1 as well as 2. So this question is based upon this equation for natural vibrational frequency. Moving to the next, read the question carefully here. In IR spectra, the carbonyl peak in salicylic acid is observed at lower wave number than in para-hydroxybenzoic acid due to. Now look at the structures of both this. This is your salicylic acid, and look at the structure of this. This is your para-hydroxybenzoic acid. Now here the IR spectra or IR peak for a carbonyl group. So carbonyl group is, this is C double bond O here. Here this is C double bond O, this carbonyl frequency. So in salicylic acid, because carboxyl group and OH groups are closer, there may be chances of hydrogen bonding. And because of this hydrogen bonding, the bond order of this carbonyl group will be altered. Here, intramolecular hydrogen bonding is not possible in this para-hydroxybenzoic acid because COOH and OH, they are para to each other. They are away from each other. But here both are ortho to each other. So intramolecular interaction is possible. That intramolecular interaction alters the bond order of this carbonyl group. So the peak, carbonyl peak, will be observed at lower wave number. Now here, because of this intramolecular hydrogen bonding, the bond order, double bond of this carbonyl, the bond order will be reduced because this electron will be involved in hydrogen bonding with the hydrogen. So bond order will be lower and natural vibrational frequency will be lower. So a lower wave number will be observed. So answer here is intramolecular interaction, which takes place in salicylic acid and which is not possible in para-amino-benzoic acid. Moving to the next, increase in ring strain shifts IR absorption wave number 2. What is ring strain? Look at this. If we consider this carbon-carbon double bond here, it is attached to 6-membered ring, attached to 4-member cyclobutane ring, attached to 3-member cyclopropane ring. Now here the bond angle is, it is a larger angle, it is 90 degree, and it is a smaller angle, less than 90 degree. So as a ring strain here in 3-membered ring is more as compared to 4-membered ring, which is still more as compared to 6-membered ring. So because of increase in ring strain, bond order also increases. When bond order increases, force constant also increases and a wave number also is higher. So here, because of the ring strain, the higher wave number will be observed. Which of the following is material of construction of optical components of IR spectrophotometer? Now, what is the criteria for the selection of material of construction of the optical components for any particular spectroscopy? That component should not absorb the particular radiation. When we are talking about this IR spectroscopy, here IR radiations are used. Now the material of construction selected should be such that it is not absorbing IR radiation or it is transferring to IR radiation. Looking at this, the glass absorbs IR radiation, quartz absorb IR radiation, polymer also absorbs IR radiation, but potassium bromide don't absorb IR radiation. It is transferring to IR radiation, so it needs to be selected. Here glass can be used in U visible region, quartz can be used for UV region. So, and potassium bromide for IR spectrophotometry. The IR spectroscopy cannot be used for estimation of. Now this is a question based upon applications of IR spectroscopy. As we know that IR spectroscopy is used for qualitative and quantitative estimation. When I say qualitative estimation, means IR spectroscopy is used to identify a particular functional group. So IR spectroscopy can be used for identification of functional group. This is a moisture. What is moisture? Moisture means it contains water, H2O. So this water absorbs the IR radiation. H2O absorbs the IR radiation. So the IR spectroscopy cannot be used for estimation of. So because IR spectroscopy can record water, because water absorbs IR radiation, it can be used for estimation of moisture also. The molecular weight. Look, the IR spectroscopy will talk about functional group, but it cannot talk about the molecular weight of any molecule. The quantity. Whether IR spectroscopy is used for quantitative estimation? Yes, it can be used for estimation of quantity. Like we have seen that a carbonyl group, suppose it shows peak, a carbonyl peak, and if we prepare standard solutions of a compound containing carbonyl group, if we increase the concentration of that absorbing species in the IR, the area under this carbonyl peak will increase, and this area will correspond to the amount of absorbing species. So this principle can be used for quantitative estimation in IR spectroscopy. So IR spectroscopy can be used for functional group analysis or functional group identification. It can be used for estimation of moisture. It can be used for quantitative estimation, but it cannot be used for estimation of molecular weight. So answer is molecular weight. Now in IR spectra, normally values on x-axis are, if you look at this, this is what is IR spectrum is. This is your x-axis. This is your y-axis. On y-axis there is %T, and on x-axis there is V bar, that is wave number. So normally on x-axis of an IR spectrum, the values given are of wave number. IR spectroscopy is a type of. Now we have seen different types of spectroscopies, like absorption spectroscopy, emission spectroscopy. Under absorption spectroscopy, again there are different types of spectroscopies are involved. Now whether this radiations causes changes in a molecule like rotation, vibration or electronic transitions, that will be decided by the energy of the particular radiation. For electronic transitions, highest energy is required, comparatively less energy is required for vibrational spectroscopy, vibrational changes in the molecule. Nuclear spectroscopy, where there is a change in nucleus of the atom, and emission spectroscopy is there is something emitted after absorption. Now in IR spectroscopy there is no chance of nuclear spectroscopy because the nucleus is not involved here. There is no question of emission because only absorption takes place. Now we have to choose in between this, whether it is electronic spectroscopy or vibrational spectroscopy. Here energy of IR radiation is not sufficient to cause electronic transitions in the molecule. So it's a kind of vibrational spectroscopy. For electronic transitions to take place in the molecule, some higher energy is required. Here the energy of UV and visible radiation is sufficient to cause electronic transitions in the molecule. So UV visible spectroscopy is called electronic spectroscopy, whereas IR spectroscopy is known as vibrational spectroscopy. Then next one, during sample preparation for IR analysis, the best diluent is water, methanol, carbon tetrachloride and potassium bromide. Again, what is the criteria for selection of solvent in any spectroscopic analysis is that that solvent should be transparent to the particular radiation, or that solvent should not involve in absorption of that particular radiation. Now here when we are going for IR analysis, we have to select a diluent which will not absorb the IR radiation. Now water, it absorbs IR radiation. Methanol, it again absorbs IR radiation because it contains OH functional group, CH bond and all this, CO like that. Water again contains OH bond. Carbon tetrachloride, CCl4. There is CCl bonding like this. So CCl bond can absorb IR radiation because there is a change in dipole. But potassium bromide, this is a salt, KBr, it is not absorbing IR radiation. So it will be the better, it is the option as a diluent for preparation of sample in IR spectroscopy. Thank you very much.